Picture this. You're walking into your Cambridge Biology 9700 exam. You flip the page and you see a massive, high-mark question on 6.2 translation. Instantly, you think, awesome, I've completely nailed this. I mean, you know exactly what a ribosome is, you know what tRNA does, so you write it all down and you walk out of that exam hall feeling on top of the world. But then, weeks later, you get your results back and you've missed a critical grade boundary. It's heartbreaking. So what happened? Why? Well, it's because simply knowing the biology isn't enough anymore. You didn't lose those marks because you didn't know your stuff. You lost them because of one tiny, totally hidden mistake in how you actually structured your answer. Today, in this explainer, we're going to fix that for good.
So, why do we see so many smart students absolutely hemorrhaging easy marks on this specific topic? It really comes down to the primary, painful mistake that Cambridge learners make year after year. Look, when you're under pressure, the brain just naturally defaults to reciting definitions like a textbook. You spot the word translation on the paper and boom, you immediately start listing off random facts about ribosomes and RNA. But here is the hard truth you need to hear. Examiners are not looking for a biology dictionary. They're looking for applied contextual science. When you just recite facts, you are falling right into their absolute biggest trap.
You don't have to take my word for it. Just get a load of this exact quote straight from the Cambridge Principal Examiner report. They say, students confuse cause and effect, providing generic answers not specific to the question context. Boom. That right there is exactly why your ordinary revision fails here. You can literally memorize flashcards for hundreds of hours, but if you step into that exam hall and write a generic answer that isn't specifically tied to the exact scenario or data they gave you, you get a 0 for that point. No exceptions. The stakes are incredibly high. But the good news is, once you understand what they actually want, you can secure every single mark.
Section 1. Decoding the core principles. Okay, so to stop providing those dreaded generic answers, we first need to lock down the exact terminology. Because honestly, mixing these up is exactly where that whole cause and effect confusion begins. We are going to decode the 4 core principles of translation right now. And we need to look at these not just as boring definitions, but as interconnected parts of a highly specific machine, where every single component has a distinct job. Think of the ribosome not just as some random location in a cell, but as the actual cellular machinery. It's the factory floor where translation and protein synthesis happen. It's the physical structure that clamps onto the messenger RNA and facilitates that entire assembly line of amino acids. If you don't clearly establish the ribosome as the site of synthesis in your exam answer, well, the rest of your explanation basically has no foundation to stand on.
Right, next let's look at tRNA, or transfer RNA. This right here is the vehicle. It is the highly specific molecule that carries the amino acids directly to our ribosome factory floor. Now I want you to really notice that word specific. A massive, and I mean massive mistake students make is just saying tRNA carries an amino acid. No way, it carries a specific amino acid. This entire biological system is perfectly organized, and examiners absolutely need to see that you understand that strict causal specificity.
Moving on, let's isolate the anticodon. Now this is where things usually get a bit blurry for students. An anticodon is a sequence of exactly 3 nucleotides forming a unit of genetic code specifically located on the tRNA molecule. Try to visualize this right now. The anticodon is literally the key attached to the tRNA vehicle. It is the core mechanism that ensures the tRNA is dropping off the correct amino acid. If you accidentally place the anticodon on the wrong molecule when writing your exam answer, you lose the mark instantly.
And that brilliantly illustrates the other half of this amazing lock and key system, the codon. The codon is the sequence of 3 nucleotides on the messenger RNA. The cross-topic connection here is absolutely essential. The anticodon on the tRNA must be completely complementary to the codon on the mRNA. This precise, beautiful matching relationship is what dictates the entire sequence of the protein. So when you explain this in the exam, you must explicitly state that the anticodon binds to the complementary codon. Don't just imply it, say it.
Now to make sure you never, ever mix these up when you're sweating under exam pressure, I've got a total game changer for you. It's a high-retention memory trick. Create a mnemonic using the first letters, R, T, A, C. Ribosomes, tRNA, anticodons, codons. Think of the phrase, read the amino code. Ribosomes provide the space, tRNA brings the goods, anticodons check the lock, and codons are the instructions. Keep that sequence, RTAC, locked into your brain before you write a single word of your translation answers.
Section 2. The method mark strategy.
All right, now that our theoretical definitions are totally bulletproof, we're shifting gears. We're moving from just knowing the biology to executing a high-mark exam strategy. This is exactly what the Cambridge syllabus refers to as handling and evaluating information. In just a second, I'm going to show you the ultimate examiner clue that changes your answer completely. But first, you really need the framework that makes that clue super obvious. Because without this framework, you'll honestly just end up staring at the exam paper, guessing what they want. With it, the specific path to top marks will basically light up on the page for you. So, this is the Deconstruct, Solve, Evaluate methodology. It's a mandatory standardized sequence for problem solving. Step 1. Identify the key elements given to you in the prompt. Just figure out what's there. Step 2. Deconstruct the data from any stimulus materials they give you, like graphs or tables. Step 3. Execute your answer using clear notation and precise scientific terminology. And finally, Step 4. Verify the context. Ask yourself, does your biological explanation actually answer the specific, unique scenario the examiner invented for this exact paper?
Think of it like this. Here is the exact concept to data pipeline examiners demand when you're interpreting relationships. Column 1 is your core concept, say, complementary base pairing. Column 2 is your evidence from the data. For example, maybe it's a mutated sequence shown in a table. Then column 3 is your scientific reasoning. This is where you explain exactly how that mutation changes the codon, which then changes the anticodon binding, which ultimately alters the whole amino acid sequence. Listen carefully. If you skip the middle step and just write the concept and the reasoning, you drop the marks. You absolutely must use their data.
Section 3. Flawed versus perfect answers.
Let's really escalate the stakes here. I want you to step into the shoes of a senior examiner for a moment and grade this. Look at the left side. We have a flawed answer. tRNA brings amino acids to the ribosome. Okay, sure, it's biologically true, but it's totally generic. It scores a flat 0 in a high-level application question. Now look at the perfect answer on the right. The specific tRNA anticodon binds to the complementary mRNA codon, bringing the precise amino acid required by the stimulus context. Wow! Do you see the difference there? The perfect answer uses hyperspecific terminology, it links cause and effect, and it connects directly to the context of the question. That, right there, is the absolute secret to moving into the top mark band.
Section 4. Critical Examiner Warnings.
We're approaching the climax of this explainer now. Here are the final traps that trip up even top-tier A-star students. These are critical warnings sourced straight from the Cambridge grading rooms. Honestly, if you ignore these, you're just leaving easy marks sitting on the table. First, confusing cause and effect. Don't ever say, the protein changed the DNA. Actually, scratch that. It's the other way around. The DNA mutation changed the mRNA codon, which then affected translation. Sequence totally matters. Second, forgetting terminology. Calling an anticodon a code thing definitely won't fly. Use the precise terms. And third, the fatal error we've been hammering on all day, providing answers that are not specific to the context.
And here we go. This is the payoff to that big examiner clue I mentioned earlier, the number A1. The absolute golden rule here is that you must provide exactly one specific contextual link to the scenario for every single point you make, period. If it's a 3-mark question, you need 3 biological facts, and every single one of them must include one direct reference back to the organism, the data table, or the specific disease mentioned in the question prompt. 1 link equals 1 mark. It's really that simple.
Okay, so you've mastered the terminology, you've completely memorized RTAC, you understand the method mark strategy, and you know the rule of 1 contextual link. Honestly, you are light years ahead of where you were just 10 minutes ago. But a hidden trap still remains on that exam paper, because knowing the biology and the structure, that won't save you if you fundamentally misinterpret what the exam paper is actually asking you to do in the first place.
So consider this final, totally crucial question. Which command words actually decide your final mark band? I mean, is the paper asking you to describe, explain, evaluate, or calculate? If you describe when you are actually supposed to explain, you lose every single mark, even with totally perfect biology. To find out exactly how to decode these tricky command words and secure your absolute best grade, you need to subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Do it right now and dive straight into our next explainer on command words. I'll see you there.